In this video, we will learn how to apply what we know about balanced chemical equations to calculate the masses of reactants and products using ratios, molar quantities, and molar masses. Now, before we dive into this topic, let's take a moment to review what we know about chemical equations. A chemical equation is kind of like a recipe that you might follow to make some baked goods. When we're following both a recipe and a chemical equation, we combine specific amounts of our starting materials to create something new. While we're following our recipe, we combine specific amounts of our ingredients, like flour, sugar, and eggs. But when we're following a balanced chemical equation, we're combining specific amounts of chemical compounds, which we call our reactants. And then the reactants chemically combine to form the products. Now, when we follow a chemical equation, it specifically needs to be a balanced chemical equation. This means that the chemical equation follows the law of conservation of mass, which is sometimes historically referred to as the law of indestructibility of matter. The law of conservation of mass states that in a closed system, the mass is constant. A closed system being something that matter cannot escape from, like a sealed container. The law of conservation of mass was famously demonstrated by the French scientist Antoine Lavoisier in the late 1700s. Lavoisier was investigating a type of reaction where a metal, such as mercury, is heated to form a new substance called a metal calx. Heating mercury, for instance, would form a red powder, which is known as mercury calx. All of these reactions have the curious property that the calx that was formed was heavier than the original mass of the metal that was started off with. But when Lavoisier performed the reaction in a sealed jar, making the system a closed system, the mass of the system remained constant. It turns out that the metals were reacting with the oxygen in the air to form metal oxides, and when you considered the mass of the metal plus the mass of the oxygen it was reacting with, the mass was in fact conserved. As we can see from looking at the balanced chemical equation for this reaction, the law of conservation of mass reflects that we have the same amount and type of atoms on both the reactants and product side of our balanced chemical equation. In chemical reactions, the atoms that make up the reactants just recombine to form new substances. This means that the numbers that are in front of the chemical species in our chemical equations, which are called the stoichiometric coefficients, reflect the amount of each substance that participates in the reaction, given in moles. So knowing that these stoichiometric coefficients reflect the amount of the substance in moles that participates in the reaction, we can calculate the total mass of the products and the total mass of the reactants for this reaction and see for ourselves that the law of conservation of mass would in fact hold for this reaction. But as a quick aside, it's worth mentioning that the conservation of mass is not actually held for all processes. In nuclear reactions, for instance, mass can be converted into energy and vice versa. A fact that is reflected by Einstein's famous equation E equals mc squared. However, for these kinds of processes, if we consider the energy and the mass together, it is held constant. But we don't need to worry about this too much, as the conservation of mass will hold true for the vast majority of processes we encounter in chemistry. So now that we've reviewed balanced chemical equations, how can we use them to solve problems? Oftentimes in chemistry, we want to know how much of a reactant we'll need to produce a certain amount of our products. Or we'll want to know how much of our product will be formed given the amount of reactants that we start off with. Or we'll want to know how much of a reactant we'll need given how much of a different reactant we're using. In other words, we need to know how to convert between amounts of chemical substances that are participating in the same chemical reaction. Let's go back to our muffin recipe real quick. Sometimes when we follow a recipe, we don't quite have the right amount of ingredients to follow the recipe as written, or we might want to scale up the recipe to make more. For instance, we might want to make 18 muffins instead of the 12 muffins that this recipe makes. Though we might have done something like this intuitively in our heads in the past, if we write out our work rigorously, we would want to use ratios to scale the recipe to figure out how much of all our ingredients we'll need to make these 18 muffins. For instance, from the original recipe, we can see that we need 1 cup of milk to make 12 muffins. So the ratio of cups of milk to number of muffins is 1 to 12. Then, to find the amount of milk that we need to make 18 muffins, we just multiply this ratio by the number of muffins that we want to make, which would give us 1.5 cups of milk. We'll follow a very similar process when we're doing calculations involving chemical reactions. So let's take a look at this balanced chemical equation to get some practice. In this reaction, we have nitrogen and hydrogen reacting to form ammonia. Instead of using the amounts of ingredients in a recipe to convert between different amounts of substances, we're going to create molar ratios using the stoichiometric coefficients from our balanced chemical equation. So let's practice this by creating molar ratios for each pair of substances in our equation. Let's start off with a molar ratio between nitrogen and hydrogen. As we can see from our balanced chemical equation, every 1 mole of nitrogen needs 3 moles of hydrogen to react, so the molar ratio between nitrogen and hydrogen is 1 to 3. Now let's look at nitrogen and ammonia. From our balanced chemical equation, we can tell that every 1 mole of nitrogen produces 2 moles of ammonia, so the molar ratio here is 1 to 2. Finally, let's look at hydrogen and ammonia. Every 3 moles of hydrogen produces 2 moles of ammonia, like we can see from our balanced equation. So the molar ratio of hydrogen to ammonia is 3 to 2. It didn't come up in this example, but it's worth pointing out that molar ratios should always be expressed as the simplest whole number ratio. So for instance, if we ended up with a molar ratio of 2 to 2 from looking at our equation, we would actually want to express this molar ratio as 1 to 1, since 2 to 2 can be reduced further by dividing it by 2. So now let's put these molar ratios to work to convert between different amounts of substances. So what amount of H2 in moles is needed to produce 4 moles of NH3? So in a problem like this, we're given an amount of one chemical species that's participating in the reaction, in this case ammonia, and we want to convert it into an amount of a different chemical species in the reaction, in this case hydrogen. We'll tackle this kind of problem just like we saw with the muffin example earlier. We'll multiply the amount of NH3 that we're given by the molar ratio of H2 to NH3, which is 3 to 2, which gives us 6 moles of H2. Notice that we want to arrange our molar ratio so that the moles of ammonia will cancel. We want to make sure that we aren't arranging our molar ratio the other way around. So now we know how to make a molar ratio from a balanced chemical equation and use it to find the amount of products and reactants we'll consume or produce in a reaction. But just to reiterate, to perform these calculations, the chemical equation needs to be balanced. Otherwise, our work just won't make sense. Now, molar ratios are incredibly useful to find the amounts of all our chemical species that we need. But when we perform chemical reactions in the lab, we usually don't know the amount of moles of a substance that we have directly. Rather, we'll usually weigh out the mass of our reactants on a balance. So we're going to need to know how to convert between mass and moles, and vice versa. We can do this by using the molar mass of a substance, because the amount of a substance in moles is equal to its mass divided by its molar mass. So if we have a mass of a substance and we want to know the amount of it in moles, we can convert between the two by dividing by the molar mass. And we can go the other way around and convert from moles to mass by multiplying the amount of the substance in moles by the molar mass. So now that we've learned all these different ways to convert between different quantities, let's sum things up before we move on to some example problems. If we want to convert between different amounts of substances that are participating in the same chemical equation, we can use molar ratios. If we want to convert between the amount of a substance and its mass, we can use the molar mass of that substance. Though it didn't come up in this video, sometimes problems will ask us to solve for the number of entities, meaning the number of atoms or molecules that are in a sample of a substance, which we can do by using Avogadro's constant, which tells us the number of entities that are in a mole. If we ever get stuck solving a problem, we can use this chart by starting with what we're given and following it around until we have the quantity that we're interested in solving for. So now let's apply everything that we've learned to some examples. Methane burns in oxygen according to the following equation. CH4 plus 2O2 reacts to form CO2 plus 2H2O. What is the molar ratio of methane to oxygen? This question is asking us to create molar ratios, which are ratios that help us relate amounts of different chemical species that are participating in the same chemical reaction. Molar ratios are useful to us because they help us convert between amounts of one substance and amounts of another. To create molar ratios, we'll use the stoichiometric coefficients from a balanced chemical equation, which refer to the amount of each chemical species that participates in the reaction in moles. So before we create our molar ratios, let's quickly ensure that our chemical equation is balanced. There is 1 carbon on each side of the equation, 4 hydrogens, and 4 oxygens. So our equation is balanced and good to go. This question is asking us to create a molar ratio between methane and oxygen. And as we can see from looking at our balanced chemical equation, the stoichiometric coefficient in front of methane is 1, and the stoichiometric coefficient in front of oxygen is 2. So the molar ratio of methane to oxygen is 1 to 2, which means that for every 1 mole of methane, 2 moles of oxygen is needed to react with it. What is the molar ratio of methane to carbon dioxide? Now we want to do the same thing, but for a ratio of methane to carbon dioxide. As we can see from our balanced chemical equation, we need 1 mole of methane to produce 1 mole of carbon dioxide, which gives us a molar ratio of 1 to 1. What is the molar ratio of oxygen to water? Now we need the ratio of O2 to H2O. The stoichiometric coefficients in front of both oxygen and water are 2, so we get a ratio of 2 to 2. But you'll notice that we can simplify this ratio by dividing it by 2, which would give us a ratio of 1 to 1, which is the correct molar ratio, as we should always express these molar ratios in the simplest whole numbers that we can. So the molar ratio of oxygen to water is 1 to 1. So now that we've worked this problem where we find the molar ratios from a chemical equation, let's try a harder problem where we apply them. Sulfur burns in oxygen to form sulfur dioxide. What is the mass of sulfur needed to produce 4 grams of sulfur dioxide? First, let's create a balanced chemical equation for the reaction described in this problem. We have sulfur, which has the symbol S, burning in oxygen, which would be O2, which is reacting to form sulfur dioxide, or SO2. If we take a quick look at the equation that we've created, we have 1 sulfur on each side of the equation and 2 oxygens, so our equation is balanced. This question gives us a mass of sulfur dioxide, and it's asking us to convert that into a mass of sulfur. But we can't go directly from a mass of one chemical species to a mass of another. So instead, we're going to have to go from the mass of sulfur dioxide to moles of sulfur dioxide, then convert into moles of sulfur, and then from there, solve our problem by finding the mass of sulfur. We can convert from mass to moles or moles to mass by using the molar mass of a substance, because the amount of a substance in moles is equal to the substance's mass divided by its molar mass. We can calculate the molar mass for sulfur dioxide using the periodic table. Sulfur has a molar mass of 32.06 grams per mole, and oxygen has a molar mass of 15.999 grams per mole, which gives us 64.058 grams per mole for the molar mass of sulfur. Now we can convert from grams of SO2 to moles of SO2 by dividing by the molar mass, which we can see from our formula, and we can also see from the fact that the units of grams of SO2 will cancel. Now we can either perform the calculation here, giving us 0.0624 moles of SO2, or we can continue the calculation on in one line. Either way, our next step will be to convert from moles of SO2 into moles of S. We can do this conversion by using a molar ratio that we create from the balanced chemical equation. As we can see, every 1 mole of sulfur produces 1 mole of sulfur dioxide. Now our final step is to convert from moles of sulfur into the mass of sulfur so we can solve this problem, which we can do by multiplying by the molar mass of sulfur, 32.06 grams per mole. Multiplying everything out, this gives us 2.002 grams of sulfur. But the mass of sulfur dioxide that was given in the problem was given to one significant figure. So we should state our answer to one significant figure as well, which gives us 2 grams of sulfur needed to produce 4 grams of sulfur dioxide. Now let's summarize what we learned in this video with the key points. We can create molar ratios by using the stoichiometric coefficients found in the balanced chemical equation. These molar ratios are then used to convert between amounts of reactants and products. Finally, we can use the molar mass to convert between mass and moles, and vice versa.